Bismillahirrahmanirrahim. Students, we are studying Electromagnetic Theory 1 with course code PHYS 3117. And today, Alhamdulillah, it is our lecture 9. And uh, in this lecture, we will discuss about the inductance and the capacitance. After studying the inductance and the capacitance, I will also tell you in detail about the distribution of the charges. I mean, after discussing these things in for a point charge, I would like to explain my all these topics for the distribution of the charges and after studying these topics, we will be able to say that we have ended our chapter 1 according to the SOS, right? And after studying that, we will discuss the Laplace and Poisson's equations. So about electrostatics, we have read a lot. After studying these topics, we have read a lot, right? And let's start. Inductance and capacitance. Okay. Before studying the inductance, we will have to find what is inductor. So, what is inductor and what is capacitor, right? And after studying inductor and capacitor, we will find that these inductors and capacitors are produced with which relations. So, which topics I will balance in these slides is one is inductor and the relationship between voltage, current, power, and energy. So, students, what is the relation between voltage, current, power, and energy? Okay, next we will read about the capacitor. And again, after studying the capacitor, we will find the relation between voltage, current, power, and energy. Okay, after studying the inductors, capacitors, their relations between voltage, current, power, and energy, we will discuss the series and parallel combinations for the inductance and the capacitor. Right? When we will put these inductors and the capacitors in the series and parallel combinations, we will have a lot of things to discuss. Students, this is an inductor, right? About this inductor, first of all, length of this inductor is L, and what you are saying, watching on this inductor are the number of turns. So the number of turns are N. A is the cross-sectional area. ठीक है? Length L, number of turns N, and A is the cross-sectional area. Okay, and what is passing from here is the current I, and what is going to be established in them is the potential. This from positive to negative. Now I would like to tell about shown you before, that is the figure of the inductor, and now I will tell you about the inductor concept. An inductor consists of a coil of conducting wires, and inductance is the property whereby an inductor exhibits opposition to the change of current flowing through it, measured in Henry. Okay, inductance is the property where by an inductor exhibits opposition. In fact, the thing to which we say this is the current is in fact produced about the opposition, right? L is the property whereby an inductor exhibits opposition to the change of current flowing through it measured in Henry. Okay, it means unit of the inductance is Henry. So that is a very much important to understand what is inductance is n square mu A over L, and these all quantities we have seen in the inductor. L is the length of the inductor, A is the cross sectional area, and N is the number of turns, and mu is what is the constant, right? So this inductance is going to be directly dependent upon n square, number of turns square, cross sectional area, and length. And after removing that proportional, we put a proportionality constant, that is mu. So inductance L is the inductance in Henry, N is number of turns, mu is core permeability, A is cross sectional area in M square, and L is the length, right? And these all things we have also seen in our figure and also discussed in our this formula. Okay. Now students, two things which are very important to understand. One is the inductor current and other is the inductor voltage. What is current? Any one of you knows what is current? Current is the charges, flow of charge, right? That is the flow of charge. So inductor symbols, we have this spring type of inductor. If we want to show inductor in any circuit, then we will say that we have this type of symbol, and we can say easily this is an inductor. So a current passes from this inductor in the form of I of t, and a positive and negative potential is established over here. Now, what is the inductor voltage? L di of t by dt, right? The amount of current passing per unit time is voltage and is multiplied with that of L. Now, what is inductor current? I of t is equal to 1 over L integral t naught to t. T naught means when from the start, and t at any time t is nu of tau d tau plus I of t naught, right? This is the inductor current. Inductor current nu of tau d tau plus this is time parameters and this is t naught. We are talking about initial conditions, and P is in fact the V into I. We will all also talk about the power. First we have talked about the inductor current, and then we will have talk about the power. So P is equal to V into I. This is V is what? Li d by dt of I. So if we take V outside then I is 1 over L integral t naught to t v dt plus I of t naught. It is power. So we have three type of terms. One is inductor current, inductor voltage, and inductor power. and it can be further written as W of t minus W of t naught is equal to integral T naught to T P of tau d tau half Li square of T minus half Li square of T, right? Assuming that energy is zero at time t is equal to T naught, then inductor energy is, this is electrostatic energy, right? W of t is equal to half Li square of t. So up to this point, we have read three types of parameter. One is inductor current, inductor voltage, inductor power, and inductor energy. And inductor energy is in fact the electrostatic energy. So students, you will get some hints. So why we talk before that about a lot about the electrostatic energy. In fact, this is the energy stored in the inductor. Okay, now let's read about the capacitor. Okay, this is a capacitor in front of you. It consists of two conducting plates, each of area A. This is the dielectric medium. Anything can be over here. This, it might be air, it might be wood, it might be water, anything else. And according to that, we put our permittivity constant. Distance between them is d. So IC is the current flowing through it, and this is the voltage. Definitely, we will have to apply the voltage between these two plates. Capacitance voltage, positive, negative, and the current IC will pass through it. And okay, lastly, we have discussed about all the two conducting plates and the medium and the voltage, etc., etc. Now we will tell about the theory. The capacitor consists of two conducting plates separated by an insulator or a dielectric. Yes, medium between these two plates might be the dielectric, right? Okay, capacitance C is the ratio of the charge on one plate of the capacitor to the voltage difference between the two plates measured in farads. Capacitance is the ratio of the charge on one plate of the capacitor to the voltage difference between the two plates measured in farad. Amount of charge stored represented by Q is directly proportional to the applied voltage V. This is equal to Q is CV. Amount of charge stored represented by Q is directly proportional to applied voltage V. Q is CV. Q is Coulomb. Students, this is written in Italian. Castellum, Coulomb, Farad, and volts. Volt and Dalem. Capacitance Dalem. Castellum, Coulomb, Farad, and volts. So, in fact, C is equal to charge per unit voltage, Q over V. We can write it according to our convenience. It might be Q is equal to CV and V is equal to Q or C, whatever you can write over here. next we move further. Okay, this is what, students, from where we have get EA. Yes. This is the permittivity. E is the permittivity of dielectric constant between the plates, and C is the capacitance. A is the surface area of each plate. D is the distance between the plates. So, capacitance. When the two plates of the capacitors are filled with any dielectric, then we say that this C is equal to EA over D, and surface area of each dielectric is represented in meter squares. D is the distance between the plates is represented in meters, and C the capacitance in the farad. Okay, what I have told you in the start is that we will find the relationship between the voltage, current, power and energy. So the capacitor symbol is this one, like this. One side straight and other side curve. I of t is the current and V of t is the voltage from positive to negative. So um, in any circuit, if we want to represent it with the capacitors, then this is I of t into C, right? We can place it. Okay. Yes. Before that, we have discussed about the conductor current and the conductor voltage and the conductor power. Similarly, we will discuss over here the capacitor current, the capacitor voltage, and the capacitor power, right? So, it is very important to understand about the capacitor current. Capacitor current is I of t is equal to C dV of t over dt. In fact, current is the time parameter dependent, and over here we have V of t is also the time dependent. So we get with I of t is equal to C dV of t over dt. So V of t is equal to 1 over C integral t naught to t I of tau d tau plus V of t naught. You can also, if you have get a note of that inductor current, then you can easily write the capacitor current and the capacitor voltage. Okay, we have the power of the capacitance, that is P of t is equal to V of t into I of t. P of t is equal to C dV over dt. If we want to find the power of the uh, capacitance, then and you can also compare it with that of the power of the inductor, that is nu of t into it. Nu of t is this one and I of t is C dV over dt. It means that is rate of voltage with respect to time. Okay, students, what thing that is very important to find is the energy density. Energy stored in a capacitor from time t to t naught. You look at this and I will explain you in detail. Here we have difference in the electrostatic potential energy in time t and in time t naught. W of t minus W of t naught is equal to integral t naught t rho of t rho of tau d tau, right? So here we put the value of rho of tau. This is mu tau c d mu tau over d tau, right? And if we arrange our all the variables, then c can we get it outside, and by arranging the variables is v gets with that of d tau, and d tau is directly cancelled with that of outside d tau. Okay, and v of tau, after taking the integration, you all know very well about the integration of this mu of tau. Mu of tau dv tau is that is v square, and apply upon it the limit of integration is from t naught to t, half cv t square minus half cv t naught square, right? And capacitor is not discharged as t is equal to minus infinity, therefore the voltage is zero. So energy of the capacitor, yeah, energy density of the capacitor from here can be derived as W of t is equal to half C nu of t whole square. This is the energy of the capacitor. And students, what I have told you earlier is that it is very important to understand the physics of the equations. So here what the physics of the equation is told is that it is directly dependent upon that of the capacitance and the potential, right? And capacitance is of the capacitor is constant, therefore going to be dependent upon the potential. Okay. Lastly, what I want to discuss with you is that we will use these capacitors in series and parallel. This is the parallel combination, right, in front of you. So for the parallel combination, here you will have equivalent capacitance C equivalent of n parallel connected capacitors is the sum of the individual capacitance of these parallel capacitors. If these capacitors are attached parallel, then total capacitance will be equal to sum of the capacitance of these capacitors. Clear? Next. Okay. Kirchhoff rules, circuital rule from the previous circuit. It is very clear. In is equal to Cn dV over dt, and I is equal to I1 plus I2. I1 plus I2 plus up to so on In, and I is equal to C1 d nu over dt plus C2 d nu over dt plus C3 d nu over dt plus up to so on Cn d nu over dt. So it will give a very good equation, that is d nu over dt is constant, and we get C1 plus C2 plus Cn into d nu over dt. Summation n varies from 1 to n, and into Cn. Equivalent equation, equivalent capacitance, C equivalent over dt. Equivalent capacitance for the parallel capacitor is C equivalent is equal to summation n varies from 1 to n Cn, and charge is going, that is Is, and what's the produce between the two ends is the potential, that is shown very clearly over here. This is the equivalent capacitance. So very clearly shows the equivalent capacitance of the capacitors. The capacitors you will attach over here in parallel, get them add, and you will add them. In fact, this is very important. Equivalent capacitance depends upon how many capacitance are attached over here, and what is the capacitance. Equivalent capacitance of n series connected. This is, students, this is series combination. Previously you have studied about the parallel combination, and this is in fact the series combination. So in series combination, this is Vs is equal to, this is potential 1, potential 2, potential up to so on. Now we will see that these will be related. Kirchhoff rules. We will use Kirchhoff rules for voltage. Voltage Kirchhoff rule is 1 over Cn integral minus infinity to t I of tau d tau, and potentials will be added up. V is equal to V1 plus V2 plus V3 up to so on Vn, and V is equal to 1 over C1 plus 1 over C2 plus 1 over Cn minus infinity to t I of tau d tau. Summation n varies from 1 to n. 1 over Cn integral minus infinity to t I of tau d tau. 1 over C equivalent minus infinity to t I of tau d tau. Equivalent circuit for the series capacitors. 1 over C equivalent is equal to summation I varies from 1 to n 1 over Cn. Vs is I. I current will pass from here. So from previous capacitance of the parallel capacitors and this capacitance of the series capacitor, difference over here is only for this one. Over there, that was only the direct relation with that of Cn. Here we have the ratio relation with that of C. Okay, next we have series and parallel inductors. The equivalent inductance L equivalence of n series connected inductors is the sum of the individual inductors. We have L1, L2 with V1, V2, and we connect them up to n times, that is Ln, Vn, and total will be given. Kirchhoff rules V1, V2, Vn, V1 diu by dt, di by dt, L2, L3, take di by dt. That's the same procedure which we have done before. So here we have summation I varies from 1 to n, Ln di over dt, L equivalent di by dt. Equivalent circuit for the series inductors will be summation n varies from n 1 to n Ln V of s, and okay, and the equivalent inductance if we put all these parallel connected inductors in the reciprocal of the sum of the reciprocals of the individual capacitance. So that is L1, L2, L3. This is for parallel. Okay, students, one thing that you should note over here is that uh, uh, there is inductor and capacitance are the reciprocals of each other. If in parallel combination capacitance is the direct relation, then in parallel combination inductance is not the direct relations, that is the reciprocal. And in similarly in series capacitance is the reciprocal combination, and in inductance series parallel combinations. Use apply the Kirchhoff rules for the current L1, I1, I2, I3 up to so on IN. You can take nu tau d tau outside, put integration this one. So this is the equivalent circuit for the parallel inductors. Capacitance. When voltage across a capacitor is increased or decreased, the capacitor resists the change. Current alters the charge on a capacitor. Capacitor is directly proportional to the rate of change of the voltage across those plates. As the supply voltage increases and decreases, the capacitor charge. DC, an inductor behaves like a short circuit, and a capacitor behaves like an open circuit. Short circuit and open circuit. Students say C for the short circuits and this is for the open circuit. Capacitor function as an open circuit at low frequencies, while at high frequencies it acts as circuits. Thank you so much, and with this slide I am very happy to tell you we have ended the chapter 1 of your SOS. After that, in the next lecture, I will do my best to give you the Laplace and the Poisson's equations. Chapter 2 according to SOS. Thank you.